Welcome back, Chemistry 30. This is the MS3.2 section, Introduction to Hydrocarbons. So we're furthering with the introduction. We're going to look at the alkane group, though, the kind of simplest one you can think of it as. So describe what the alkane hydrocarbon group consists of, state some common everyday uses of alkanes, describe what structural isomers are, write the molecular and condensed structural formula, and the IUPAC, International Union of Pure and Applied Chemistry. Name for alkanes that are straight chain or branch chain alkanes. Describe what cycloalkanes are, so cyclo, cycle, circle, and describe some common reactions with alkanes. So since carbon compounds are so numerous, it's convenient to organize them into families of similar structural similarities. The simplest class of organic compounds is the hydrocarbons. Ones that are, just as the name implies, made up of carbon and hydrogen. The key structural feature of hydrocarbons and most other organic substances is the presence of carbon-carbon bonds. So carbon is the only element capable of forming stable, extended chains of atoms through single, double, and triple bonds. And of course it's a small atom too, because there are other atoms like silicon that also have 4 valence electrons that they can share, but carbon, since it's the smallest, that nucleus will have an effect on outer electrons, being able to pull them in particular those shared electrons. There are 4 basic types of hydrocarbons. So alkanes, which is the one we're going to look at in this video, in this section of MS 3.2. Then we'll look at alkenes, then alkynes, and then aromatic hydrocarbons. Each type of hydrocarbon exhibits different chemical behaviors. The physical properties of all 4, however, are very similar. So if we look at alkanes, this is kind of a 3-dimensional view. So how you're aware of how this works. We have this little kind of like triangular pieces. You have to envision that as coming out towards you like this pencil. So kind of like that, coming out. Ooh, 3D. And a dotted triangle means it's going away, so going to the back end of the molecules, like how the pencil is now, going backwards. Whereas something like this would just be going straight up. So it's kind of a 3-dimensional drawing. We're trying to represent 3-dimensional drawings on this, you can think of it as 2-dimensional piece of paper. And you'll notice here that we have a tetrahedral shape, so carbon bonded to 4 things. This carbon bonded to 4 things, so it makes a tetrahedral shape. So that's the first one we're going to be looking at. So the physical properties are very similar. Hydrocarbon molecules are relatively nonpolar because, remember, the CH bond virtually is nonpolar. Like it's kind of on the weak polar scale, but mostly we can think of it as being nonpolar. So not only nonpolar, but insoluble in water, but dissolve readily in nonpolar solvents. So of course, the force that exists, the only force that exists with nonpolar molecules, of course, is dispersion forces. So if we have an alkane dissolved in a nonpolar solvent, high molar mass, high dispersion forces, that's how it can be dissolved. Also, their melting points and boiling points, as I mentioned, London dispersion forces or just dispersion forces. So depending upon how large the molar mass is. So as a result, ones that have a low molar mass, such as C2H6, are gases because there's the electrons that are going to get rearranged and make temporary dipoles. It's really small. But if we get larger and larger molecular weight, so for example here, there would be a lot of electrons that could potentially end up on one side of the molecule at once. So very difficult to pull them apart due to those higher intermolecular forces. So they tend to be solids, whereas the lower molar weight are liquids, and the really, really light ones are gases. So that's how that makes sense. Because of the larger dispersion forces, it means we need more energy to pull the molecules apart, because they're really attracted to each other due to all those electrons rearranging themselves and causing temporary and induced dipoles. So large molar mass, solids. Lower, gases. And kind of in between, we would have liquids. So looking at the alkane group, alkanes are hydrocarbons that only contain single bonds. They are also known as saturated because if they just have single bonds, they will have the most number of hydrogens that they can possibly have. So they contain the maximum amount of hydrogens. So if I have two carbons that have a single bond between them, so this carbon shares one to get one, same thing with this one, that means there's room for 3 hydrogens to bond to each of these carbons. So that's the simplest form, and it also represents a saturated hydrocarbon because it would contain the most number of hydrogens that it can possibly hold. So this is ethane, carbon-carbon, and the H's. Lewis structures of alkanes can be seen below, as well as the more convenient condensed structural formula. So if I look at 4 carbons bonded to each other, methyl, ethyl, propyl, this is butane. So carbons bonded to each other, and then just looking at what's left over here for each carbon. So that every carbon is sharing 1 electron to gain 1. So you can see share all of these. There's 4 bonds with each of the 4 carbons. Now when we get to bigger molecules, this can be kind of overwhelming to look at, all those bonds. So sometimes it's simplified to this. So we just show the carbon-carbon bonds. And we know that this carbon's bonded to 3 H's, so we'll just show it like that. Same thing with this one, bonded to 3 H's. Then the interior carbons are each bonded to 2, so we just simply write it shorthand like that, saying that, so this bond isn't attached to the hydrogen, it's attached to the carbon. But the H's just imply that, yeah, there's H's attached on the outside. And sometimes these bonds are not shown either, and we just simply write it like that. So the edge carbons would have an H3, and the middle ones would have an H2. So sometimes it is written like that. So that's something to be aware of. Now another thing, you'll get a copy of this on a colored sheet, kind of a rundown of the first 10 carbon molecules that we can have. So 1 carbon, 2 carbons, 3 carbons, and then the required amount of H's in order to make it complete. So 1 carbon, methane, 2 carbons, ethane, 3 carbons, yes, propane, barbecue tank, and butane, lighter. And then 5, we kind of go to the prefixes that we know about from looking at covalently bonded molecules. Pent is 5, hex is 6, hepta, octo, nona, and decane. So these ones we kind of know already from previously. So these prefixes are kind of new. Methyl, ethyl, propyl, butyl. So we're going to have to look at those. And notice boiling points. So if we have light versus heavy, and then average. So remember we talked about lighter molar masses. The dispersion forces aren't as big as when we get down to here, and the dispersion forces are large, meaning that to go from a solid to a liquid is going to require a lot of energy, implied by the large boiling point. So boiling point increases as we go down a group here due to larger molecules. All right, if we look at common uses of alkanes, so we can start off with the smallest one, methane, then move on to propane. Let's see, so 1, 2, 3, 4, 5, 6, and then, that's propane, which should be C3H8. Butane has 4 carbons and 10. So methane, of course, methane is a component of natural gas and is used for home heating and gas stoves, so a methane burner. Propane, of course, barbecues, right? The major component of bottled gas used for home heating and also cooking with a barbecue where natural gas is not available. So if you have a natural gas outlet in your house, maybe you don't need a propane barbecue, but for the rest of us, we do. Butane, of course, the gas that goes in, the fuel that is used for disposable lighters and in fuel canisters for camping, etc. Lanterns also use that. If I go higher than 4 carbons, so 5 to 12 and more, they're molecules that are constituents in making gasoline. All right, I think what I'll do, we're almost at the 10-minute mark, so I'll stop there. Then we'll come back and look at the structures of alkanes, different versions or structural isomers, and then we'll get into naming and writing the formulas for them.